So thanks for having the opportunity to talk today about ice sheet modelling. It's a shame Felicity's crook. She probably would have given a different talk to me. Just to note, ice sheets aren't formally part of ACCESS-NRI, and the way that ice sheets are incorporated into CMIP is an interesting. There's several interesting approaches that I will briefly talk about. But I would, just before I kick off, like to say that Felicity and I, we were asked to co-chair the community working group on cryosphere. So we've got the new logo at the top here that Natalia has been busy helping organise. So stay tuned. We'll get in touch about what the next steps for that group will look like. We've had some preliminary meetings already. It's only very early days, of course. So hopefully that slide's advanced okay.
Yep, all good.
Yep, that's great. It's probably to switch backwards and forwards. So there's several strategies, or three strategies really, for how ice sheets are incorporated into climate. The first one of those, which is the kind of current CMIP approach, is the freshwater runoff. We heard Adele speak briefly about that. There's a plot here on the right showing a sort of cross-section of the ice sheet runoffs added into the models. How it has been done is that's a surface runoff. So any accumulation that falls on, if this is Antarctica or Greenland, immediately exits the continent and enters the surface of the ocean, MOM6 coming. This is a more sophisticated treatment that I think is still useful to do. So this is being done with MOM5. So Pedro's doing some of this stuff where runoff's being distributed at depth, and that allows you to do the proper both heat and fresh water budgets. I think we're finding that that's very important to do, and it does change things a lot, particularly bottom water formation processes and how the mixing processes on the continental shelf work. The second strategy is running a MIP called ISMIP, ice sheet only models. So ISMIP's the ice sheet modeling and comparison project. The ocean-driven melt is parameterized, so you take climate model output and you sort of downscale it, if you like, to regional models. Greenland's a bit more sensitive to atmospheric driving than Antarctica. Antarctica is really driven by the ocean at this stage, but in any case, it doesn't matter. You run those by themselves and you're downscaling offline from the climate models. And so we've contributed to ISMIP with an Australian contribution. I'd like to see more mention of ISMIP in people's acronyms when they put these slides up. I think it's a pretty significant high-profile activity that we have been involved with, and it's really setting the scene for, I think, how we will eventually get ice sheets into the Australian coupled climate model. The third strategy, this is the holy grail. This is kind of where everybody's been going. Coupling ice sheets with climate. So two-way interactive coupling. That's really illustrated on the bottom left-hand side here. There's lots of different processes. We get the bottom melt. We heard Adele talk about the cavities to get the retreat of the grounding lines and the erosion of the ice. The ocean model does need to know about what the dynamics of the ice is doing, because that really determines what the profile of the base of the ice looks like. So as we know, this is the future projections from AR6, preaching to the choir here. I realise there's a couple of different storylines. There's this medium confidence future projections of sea level, and then there's this low confidence, high impact of ice sheet instability projection of sea level. These medium confidence ones are the ones that decision makers use. This one's like, well, what the hell do we do about that? That's just far too uncertain. It could mean that sea levels at the moment greater than 15 metres can't be ruled out by 2300. A lot of that's basically got to do with deglaciation of first Greenland and then Antarctica. Because of the collapse of, that's even going to want to play a movie, that was the collapse of the Larsen ice shelf. So we know that this happens. We know it leads to an acceleration of, it's actually not playing, acceleration of inland flow of the ice into the oceans and subsequent increase of sea level rise. We've just got to be careful what we mean when we talk about bringing ice sheets into an Australian climate model. This plot here is an observed GRACE follow-on mission fingerprint, if you like, of sea level changes on the planet in millimetres per year. And what we actually experience here, what we can actually detect from the GRACE follow-on mission is a drawdown in sea level around Greenland and some of the West Antarctic ice sheet and an increase in all these very dark red areas, particularly around the Australia, North Australia, and the Pacific Islands, actually, which is interesting. Now, the reason that you get a drawdown around Greenland and the West Antarctic is because these ice sheets are shrinking. And so if you look at the insert here, this top plot shows if you're shrinking your ice sheet, you've got a solid Earth adjustment process as well. But overall, the mass of that area with the ice sheet has got smaller. And so then the ocean's not attracted to it in the same way. And so you actually get a drawdown adjacent to the ice sheets, and you get a far field average increase in the rate of rise. So from the perspective of Australia, it's called gravitational far field impacts. From the perspective of Australia and the Pacific, the deglaciation of Greenland over the next decade is probably something that we need to be more considered about, and the West Antarctic ice sheet, than perhaps even what's happening in East Antarctica. East Antarctica is not showing any of those substantial changes in the GRACE signal yet. It's starting to. We've got to keep an eye on what that's doing. And this is all useful information as well to be calibrating what the climate models are doing. But if we're talking about coupling ice sheets into a climate model, then perhaps we'll also be needing to think about, well, how do we deal with these gravitational self-attraction problems, and do we need to be bringing in the solid Earth into the coupled system as well? So I'd like to talk about CMIP7 for a little bit now. Like I said, we've invested a fair bit of time in doing this, and I'd like to illustrate here some of the problems with the sequencing between the CMIP and some of these other spin-off MIPs, particularly ISMIP in this case. But this is the 5th assessment report fed by the CMIP5 RCP scenarios. That, of course, led to what was CMIP6 deck and these shared socio-economic pathway scenarios. We were desperately keen to be able to use climate model output from CMIP6 to force the ice sheets at that time. Those model outputs weren't available, so we had to make the decision to use CMIP5 outputs to force the ice sheet models. So they were forced using RCPs. These two things led into the AR6, so the 6th assessment report basically uses the ice sheet models forced from the CMIP5 deck, which is a bit unfortunate. But what happened after that, just because of the timelines, we sort of have these artificial timelines. What happened after that was there's a separate set of experiments that we're now running called ISMIP6-2300, where we're running those further forward in time, and we're using the CMIP6 outputs to help force those. So there's a combination of activities going there. Where are we going with this? And what does it mean for the Australian community? I think, again, like I said, there's 3 strategies that we need to be adopting because of the state of things. The full integration of coupled ice sheet climate models is going to take time. There's other work that we can be doing in the meantime to help consider the impact or the effect or the interactions with ice sheets. One of those is dry models by ice sheet mass loss, more sophisticated runoff. Standalone ice sheet models, I think, still critical to be doing. So basically doing regional downscaling and closing the sea level budget offline. And then the third thing is, in the meantime, we could be making progress towards that fully coupled system. So our contributions, as I said, into the 6th assessment report is CMIP2100, and the stuff that we're doing now, we used ELMA ICE, which is a very sophisticated, it's called a Stokes model. It allows you to basically model all the stresses in the ice sheet. A lot of the other contributions don't have that ability. This is the Antarctic domain. We didn't make Greenland contributions because my focus. And it's a coarse resolution for the earlier stuff, and it has a particular basal parameterization. It doesn't matter about this form, but we downscale the climate model, ocean temperatures, to of the ice shelves, and see how they evolve over time. The ISMIP6-2300, as I said, that's transitioning to the CMIP6 output. In this particular case, we decided to go for a higher resolution near the Greenland, so we brought that down to 1 kilometre. But for computational reasons, we have to use ELMA in what's called a shallow shelf approximation mode. But the cool thing about ELMA is that you can run it in full Stokes or as a Stokes model, or in this shallow shelf approximation. We're currently trying to figure out how to be able to run ELMA on Gardi at high resolution using full stokes.
Just 1 minute.
So these are all the models contributed. Sorry,
just 1 minute warning.
2 minutes. 1 minute. Yep. These are all the models that contributed to CMIP7 2100. The one in red here is us, Elmar. So we were the only Stokes model that contributed results to that. This NCAR CISM is the one that's being considered to couple through NUOPSI into MOM6. This L1, L2 is an inherently unstable stress balance model. Exactly how that's treated or if that's a consideration for Australia, we need to keep chatting about as a community. This is just highlighting CMIP5 here and CMIP6 results. This is the hot off the press Elmer Ice results. This is our Australian contribution again to the CMIP6 2300. In terms of sea level contributions for 2100, you can see there's not much difference between the two different sets of ensembles for different climate models. As we get further away in time, the East Antarctic ice sheet and even the response of the West Antarctic ice sheet is dramatically different between the RCP or CMIP5 and the SSP CMIP6 results. And we are working on coupling. So we do have a fully coupled ice sheet, Elmer Ice and ROMS ocean model. And we're talking with the GFDL team about how we can bring in MOM6 into this coupling framework as well, which is we're fairly sure compliant with NUOPSI. So that's my talk. Thank you. So just concluding points here. Really we need to know how fast and by how much will the shrinking ice sheets cause the freshening, circulation, changing of the ocean and sea level rise. Greenland and the West Antarctic ice sheet so far has the biggest potential impact. We need to think about Greenland. We can't do this problem without thinking about Greenland. There are many uncertain processes that we need to be thinking about in that, like I said before, crevassing, surface melting that brings in the atmosphere, albedo feedbacks, accumulation, hydrofracture, solid earth. They're all things that we need to connect with the fine scale modelling and the observations that we do into the climate model activity. And the future CMIP strategies I suggested that we need to be adopting all of these is the running the forward climate models, ACCESS-OM type or ACCESS-OM3 with the better representation, ice shelf cavities or runoff, standalone ice sheet models, and then working towards the coupled. Thanks very much.